In the last lesson, we learned about SUVAT equation, where they came from when we're looking at constant speed or constant velocity. In this screencast, we will learn about the SUVAT equations when we're dealing with acceleration. So here we have a simplified version of a word problem we might face. We have a car starting from rest, and that's critical information that it's at rest. If it's at rest, that means the initial velocity, v0, is 0. That's important. Oftentimes the numbers we need are not contained or written down in numbers, they're contained in words. It's 1 meter east of the easy pass. We have an east-west situation. East positive, west negative, and we have a 1 meter east. And so that 1 meter east is the initial position, XO, which we can see is right here. So here's the easy pass booth. Whoops, looks like the person went past the easy path booths, and they're at rest, 1 meter past. They're going to accelerate uniformly. Accelerate uniformly means constant acceleration. And this is that key phrase that renders all of the SUVAT equations usable or not usable. Because it's uniform, it's constant acceleration. It's constant acceleration. Therefore, we can use the equation. So it starts with an initial speed of 0. v0 equals 0. And now it's going to accelerate at 2 meters per second every second for 5 seconds. So let's think about that. It's going to go eastward. It's going to get faster eastward. So it's going to start out slowly, and then it's going to go faster, and then it's going to go faster, and then it's going to go faster still. Each time interval it's going to cover increasing ground. We know the acceleration is positive 2 meters per second squared. It's positive because east, positive, is the direction it's getting faster. And we know this is going to take place for 5 seconds. So we can see the final position is going to be well off here to the east. Now we don't have any equations that we can use to solve this problem. So we're going to start right out examining what we can get from the graph by plotting the graph. Now we know in the beginning the initial velocity is 0, and after 1 second the velocity is 2 meters per second because it's accelerating at 2 meters per second every second. So it starts at 0, and after 1 second it's 2 meters per second. And the next second is going to increase by another 2 meters per second. So it'll be a speed of 4. And in the next second it's going to increase by another 2 meters per second. And in the next second, it's going to increase by another 2 meters per second. So we're at 4 seconds, and the 5th second, it's also going to increase by another 2 meters per second. So what we can see here is this is the graph of the velocity over time, increasing. That's acceleration. Now, we have our 3 things, our bits of information we can glean from any graph, and the first thing is what we can read, and what we can read is velocity and time. The gradient we've already learned in a velocity time graph is delta v over delta t, which is the acceleration, and the area is the displacement, which is delta x. So if we want to find the displacement and ultimately the position, we need to find the area. So for the first 5 seconds, we have an area that's underneath a triangle. Underneath the curve is the shape of a triangle. So we're looking for that area right there. Now, as we begin to look at this, well, first we want to describe the velocity. Remember, in the previous lesson, we talked about equations for the velocity and the position displacement. Now, we can see the velocity is a straight line. So we have y equals ax plus b. The y-axis is velocity. A is the gradient, and the gradient happens to be acceleration, which coincidentally has the same letter A. The x-axis is time, and the y-intercept is 0. It's a direct relationship. So we have an equation that describes a velocity that's equal to at. Now, what we're going to do is we are going to look for, in the SUVAT realm, we're going to look for the area. And the area of a triangle is 1/2 base times height. So we have 1/2 the base. Now, of this triangle, what's on the base? The base is time. And the height of the triangle is the final velocity, but everywhere along this triangle, the height is the velocity. So 1/2 TV. But we know that V is AT. So we have area of the triangle equal to 1/2 T AT. Combining like terms, we get area of the triangle is equal to 1/2 AT squared. And that is the displacement. So we have S equals 1/2 AT squared, a new equation. Now to solve S equals 1/2 AT squared, well, for now we'll leave it as S equals 1/2 AT squared. Next, let us consider the more advanced formulas. And if we look at the velocity equation, V is our advanced, A is advanced letter, T is its advanced letter. So V equals AT is the same for advanced as it is SUVAT. So if we have the area of the triangle equals 1/2 base times height, the base is time, and the height is AT. So for the advanced equation, the area of the triangle is also 1/2 AT squared, and that is delta x. The displacement is 1/2 AT squared. So now if you look at the SUVAT equation and the advanced equation, they look exactly the same except for delta x and s. Now to compute the displacement, we have 1/2 the acceleration, which was given as 2, and the time is 5. So we have a displacement of 25 meters. So the position will have changed by 25 meters. If we go back up and look at the number line, it started at this position 1, and its displacement is going to be 25 in the positive direction. We can see that it's going to end at a position of 26 meters. So now to examine the position. We have the displacement, which is 1/2 AT squared. And we know to get the position, we must add in the initial position. So we get x equals 1/2 of 2 times 5 squared plus 1. So x is 26 meters. Position is 26 meters. The displacement is 25. So now let's take a look at our equations to summarize from this lesson. With the SUVAT, we have S equals 1/2 AT squared. More advanced is delta x. What we know is that delta x is equal to x minus x0. And if we add x0 to both sides, we'll be left with x equals 1/2 at squared plus x0. So we can get the position. Again, something we can't get with the SUVAT equations. And for both equations, here's something that's a little bit new. The velocity is at for acceleration when it starts at rest. We spoke about the gradient as being the acceleration of the velocity time graph. In both cases, we have delta v over delta t. For the SUVAT side, we've got v minus u over delta t, and for the more advanced side, it's v minus v0 over delta t, are the acceleration equations.